Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
So my name is Lucy van der Wende, and I have the pleasure of introducing Chris Biemann. And the purpose of the presentation is first and foremost to introduce Chris and his work to a much wider audience than he would otherwise be able to reach by having one meeting at a time. Chris comes with Powerset and has come from Powerset, but only joined a couple of months ago in January. So, quite recent, having finished his PhD at the University of Leipzig end of last year. And I'll say that there's another purpose which would have taken place anyway, because as a group, we've been very much interested in what Chris is doing on unsupervised modeling of language. And so this talk would have been, we would have hosted Chris no matter where he was. It just happens that he's now a member of Microsoft, so that's fun. But when I heard that he had gone to Powerset, I'm like, that's too bad. I didn't know Chris was looking around, because I was going to talk to him about maybe doing a postdoc here. So here he is, and we're very happy to welcome Chris to Microsoft.
Thank you very much, Lucy. Thank you for the introduction, and thank you for coming in so large numbers, which I would not have expected, frankly. So I'm here today to talk about some recent work our group in Powerset has been doing on word sense induction and word sense disambiguation. And this purpose of this talk is twofold. First of all, I want to tell you all these nice things that we pursued and these nice ideas we have and how we try to evaluate them. But the other purpose is to get you excited about this new platform you just bought at Microsoft, which is the Powerset natural language search platform, and which could be used to plug in many things you probably might not have dreamed of, given the situation before you bought Powerset. So I hope that this will trigger a lot of discussions and talks in the remainder of the day and in the weeks to come. So this is the outline of my talk. I want to make a case for word sense disambiguation in search, and I want to stress the necessity of this natural language processing step that has been neglected in search by telling you why we all think Powerset that this is important, especially if we are in the situation of semantic search as opposed to keyword search. Then I'll stretch a proposal out which consists of two basic steps. One basic step is to induce a word sense inventory, so to take the senses and the model of senses from the corpus you actually apply your methods to. So in this case, in our case, it's Wikipedia. In the broader sense, it would be the web or some subdomain or whatever you want to apply this to. This will involve graph clustering on a distributional thesaurus. And once we have that inventory, and this inventory will also give us the clues with it how to disambiguate things in context, we will be able to build a word sense disambiguation component that is able to assign the correct sense out of that inventory to actual occurrences in the text. What we did in the first place was to set up a bag of words-based system, very simplistic, and to evaluate that. And I'm going to show you these results. And since they were very encouraging, we set out to build a variety of things. We decided to use the grammatical relations we get from parsing the whole Wikipedia, and using these to build a distributional thesaurus to get more fine-grained and better distinctions, and also to shrink the amount of data we need to get nice results. You can always do more NLP and have less data, or you can always increase the size of the data and have less NLP. I'm going to talk about how to build an evaluation corpus. It's not that it's not out there, but we work on Wikipedia, not on Wall Street Journal or the news, so we don't want to use SemCore, we want to use our own corpus. And we found a pretty easy and cheap way to build an evaluation corpus for word sense disambiguation. And in the end, I'm going to give some outlooks, further ideas, and conclude. So why isn't there anything like a word sense disambiguation component in a standard state-of-the-art search engine? Well, first of all, what is the problem? Well, we have a bunch of words that are ambiguous in every language. I mean, there's various ways they can be ambiguous, but one way is the semantic ambiguity. So some words have multiple senses. The case of case. A case could be a container, it could be a lawsuit, it could be grammatical syntax case, and whatever kind of case. So if you see that word, we don't know what that means. And mostly what we observe is that the frequency distribution of the senses is highly skewed, both in our collection and in query logs, if you use it in the search engine. And the skew doesn't necessarily match. So sometimes people overwhelmingly ask for that one sense that is very rare in the index. Another problem is that it's almost impossible to determine the sense the user meant when he's querying the index from that very short keyword query. But what is most compelling and what's mostly seen as the reason why this never really got successfully implemented is what Sanderson called the query word collocation effect. And that is, the longer your query is, the more you have the effect that the ambiguous words disambiguate each other. So if you query for case, you get this part of the document space that contains the word case. It's a very simplistic view, but if you query for court case, well, you get the overlap between court and case here. And this is definitely not the overlap between plastic case, or like to carry a case. So while it's easy to get ambiguous mixed results by entering one word, it's pretty hard to get these mixed results with 3 or 4 words. So if a user sees in the result that it's too mixed, to just enter more words and disambiguate that query. But this does not work if we are in the semantic search world, and especially in the semantic search we're doing at Powerset, which is expanding the index. So very rough overview. What we do at Powerset, we don't only store the keywords, we also extract predicate argument structures, and we also expand them semantically with synonyms in various ways. So it's really nice that you can get results like these. For the question, who did Microsoft acquire? We said like something was purchased by Microsoft, somebody sold something to Microsoft, and these are these recall gaining nice matches we like. But of course, if we don't do any disambiguation, we might get spurious matches. So if we ask in today's system who studied in prison, we get results about colleges. Because for some obscure inventory, in this case WordNet 2.1, uses college as a British slang word for prison. And you always have that effect, right? No matter what inventory you need. So if we draw a picture here, what you, and this is a little bit constructed, but what you get for a query of carry case is case would not only get you the documents that contain case, but also other meanings like suit case and lawsuit. And carry would be also eliciting like documents that contain expect, because of that obscure meaning of be pregnant with somebody, and these 2 words have. So if you query carry case and you get back expect lawsuit, users will not understand this. And this is partly a reason why our ranking function does not score semantic features as highly as you would like them to be. So yeah, let's see how we can tackle this problem, how we can repair that. And what I'm proposing here is something that is not quite standard to word sense disambiguation literature. Usually what you see is there is this inventory, usually WordNet, and there is this training corpus, usually SemCore, and we want to make a system that assigns senses from that inventory to words in the text, and there's various ways to do it. And if you evaluate that, the best systems are in the ballpark of like 75%, which is clearly not enough to sort out these kind of problems. And part of the reason is that this inventory is not meant for word sense disambiguation. WordNet was not constructed for search. Another reason is that so the structure of WordNet itself, it's too fine-grained mostly. Another reason is that the resource WordNet does not necessarily match your underlying corpus. So if you go to biomedical domain and use general purpose WordNet on it, you're going to get like horrible results. If you go for a most frequent sense baseline or something like that. So the way we want to go is to first induce the senses from our collection and then to disambiguate them. And the nice thing is that this is language and domain independent as long as we have the NLP machinery to provide the features we need here. We don't have that inventory mismatch because that is performed on the same corpus. So you would restart that process whenever you have a new domain. And you have very little or almost non-manual work on lexical resources in inventories, which makes this method really cheap and quickly applicable once you have set it up. And well, setting it up is not that trivial, but we're working on it. So quite early put on the following prototype. For our collection, I'm sorry, this is very texty here, but I'll give you kind of an intuitive overview. For our collection, we computed significant co-occurrences, so words that come up together in sentences more often as you would expect if you would assume that they are independent, and that uses their frequency counts and some significance measure. In this case, it was log likelihood with some frequency threshold, so Bob Moore knows exactly what I'm talking about and why you need the frequency threshold here. So once you have all these co-occurrences, you can view this as a co-occurrence graph where every word is a node and they're connected by a weight, which is the significance of their co-occurrence. And some words will not be connected. And now, if we have a word we want to induce an inventory of senses for, we locate this word in this graph, take the whole neighborhood plus the connections in that neighborhood, and apply a graph clustering method. And hope that these clusters represent different usages of words. I wouldn't call it senses, and I'm going to have an example in the next slide to show you what the difference between senses and usages is. So once we have these clusters of words that co-occur with this word in different usages, we can use these clusters to determine what sense is present in a given context, in a given sentence, but just comparing the actual context to this kind of global sense contexts. So this is an example from the British National Corpus for hip. And there's a lot of words co-occurring with hip, and these colors are like classes as returned by the graph clustering algorithm. And what we see is, okay, there's two big meanings of hip. One is like the body part hip, and one is the music kind of hip. So here we have a word like hip-hop, reggae, soul, cantaloupe, mainstream, album. Here's hip hip hooray, it's my favorite one. And these things fall into like a body part meaning as in clothing, and this is more medical, and this is like sub-meanings of medical, this is some boxing position. So what we see here is very fine-grained. It's like different fields where hip is used, but it's still the same hip, you might think. And once we have this and sentences are coming in, we can compare these sentences to these clusters and have some kind of like trigger words that put these sentences into a class. So this sentence, for example, at his hip he wore a pistol, an ancient leather holster, and we find these words here. So we clearly know that this sentence belongs to this cluster. Sometimes we have sentences that could belong to 2 or more, and these are actually all original sentences with a high overlaps. So here we find acid jazz and reggae, and this is a very simple view how one could approach this and how would do it. That would not tell us yet what words we are able to substitute with hip, right? So this is not the full story here. But it's at least a step towards it, because if you don't know what are the distinctions, we can't decide what to substitute and when to substitute with different things. And it's not trivial, because hip in a medical sense is probably replaceable by its Latin term, but hip in a clothing sense is, in a clothing usage, might probably not be appropriate. So we set out to evaluate this, because like colorful clusters are nice, but numbers are better for that. And for that we used Amazon Turk. So it came up in an earlier meeting today that not everybody knows what that is, so let me explain it to you. That's a service by Amazon, and what you could do, you could put up human intelligence tasks that would be solved by artificial intelligence, which is basically humans performing stupid tasks that could probably be performed by computers. And you give them something like this, so that's what they see. This is a task, these instructions, and we ask them a question like, are these words used with the same meaning or not? And we give them a pair of sentences that contains the same word. I know you can't read it, but and we let them decide whether this word has been used in the same sense, in a similar sense, in a different sense, or maybe they cannot tell. And we did that for groups of 5, so each question was asked for 5 different people. That makes sense because people get paid for that. Not really much. It's ridiculous how much they get paid for that, but still people tend to click randomly, so you would level that out. It's not high quality annotation, but you can always get good mileage by giving it out to more people. And what we found is if the clustering said it was the same usage, Turkus came back with over 93% saying, yeah, it was identical or similar usage. Whereas if the clustering said it was different, it could as well be identical or different. So what that tells us, the clustering splits too much in a way. But that is not critical as long as we get our substitutions right later. So it would be much more critical if things that are not similar end up in the same group. And yeah, this might give you an idea of how good the single Turkers are. So this is for all judgments, and this is for the majority vote. And the signal for the majority vote is much better than for the all judgments. Yeah, and we use that a lot at Powerset, that Amazon Turk approach. And I'm going to show you some more of these tasks later. But okay, so we were encouraged by that. And we decided to start a project we call SenseInator, which is a kind of Powerset naming scheme to call anything with an inator. So we have a Belushinator and we have whatever inators. And this is like the 2-sentence big picture, and what you see in green here is the components we use for that. So what we set out for is to use grammar features, because we have this nice XLE parser. And we distinguish word usages, which we do by this graph clustering. And we don't do that along co-occurrences, but along words that are contextually similar to other words, so have a high distributional similarity. And that's a distributional thesaurus. Once we have this clustering, we compute global features for these clusters. And these characteristics we use for disambiguation by mapping, like measuring the overlap between cluster and document, or a larger chunk. So we don't necessarily want to go for single sentences, but we can go for several sentences and just disambiguate if we have enough evidence. So there's a one sentence per discourse assumption hidden here. And since, colorful clusters are good, but control is better, we want to measure the quality against an evaluation set, which we obtain by collaborative tagging. So we're going to use Amazon Turk to get an evaluation corpus like that. And in the remainder of the talk, I'll dive into all these points. And it's a pity that you didn't buy us a little later, because it's not quite finished yet, but we're working on it. So first of all, what is our document representation? We don't do bag of words anymore. We have these grammar features. Now we do tuples. And a document is represented by like glued together tuples that are extracted from grammar relations. We have relations between the same part of speech, between different part of speech. We treat verbs in different subcat frames as different words, which makes sense when trying to disambiguate words, because there's a high correlation between subcat and meaning. And how would that look like technically? So this is a sentence: while leaving the facility briefly, she quickly returned on February 22nd. And I just highlight the tuples for these three words: leaving, facility, and she. So what we get back from that is that this is an article about Britney Spears. It was sentence number 126. And for the word facility as a noun, and please ignore this funny separator characters, we have a feature. This word has been object of to leave in verb subject object subcat frame with a frequency of 1 in that sentence. So you could think about like aggregating over articles and having higher frequencies here. Vice versa, the word to leave in that subcat frame as a verb has a feature that facility was in an object position. And she as a subject, and vice versa, for she we have that feature. So this is how we transform our documents in the first place. And this, of course, gives us a much more fine-grained view on language than we would have obtained by bag of words on a sentence level, where we could not be distinguishing between she and facility with respect to leaving. And from that we compute a distributional thesaurus, which is pretty much a standard component that you compute from distributional similarity statistics. So you compare words along common context. And unlike another thesaurus, you have for each word a ranked list of entries. So it's not that there's a node that is populated by a bunch of words as in Microsoft Word thesaurus, but it looks much more like this. For example, meeting, the entry for meeting would have a gathering with a rank of with a score of 56, and seminar with 49, and going down like this. And you should cut off somewhere maybe. So there's a lot of parameter space to explore. And these words are not synonyms, and these words are not substitutable. So sometimes they are. Meeting and gathering is a good one. But if you query for PowerPoint, you don't want to get Excel, right? You want to get PowerPoint. So this is just a word that behaves similarly. And what we see in the PowerPoint, something maybe unexpected, there's a couple of file formats here, because you could save something in the PowerPoint format. So that's a different usage. So PowerPoint is ambiguous. You would have thought that. And this is how we do it. This is how we arrive from a text, which broken down into these kind of tuples over a couple of steps to a distributional thesaurus. There's a bunch of parameters here. We compute significance between pairs, because we don't want to have features that apply to everything, like large as an adjective. Many things can be large. There's some pruning, And there's some trick here that avoids comparing each word to each other word. So you might think like if you have 1 million words, we have to compare like 1 million words to 1 million words. This matrix is even too big for parallel computing. But we shortcut here a little bit by using the fact that this matrix of similarity will be sparse, and we just compare things that have at least one feature in common. And all these boxes, all these steps are implemented as MapReduce jobs. It's a little bit like Cosmos and Scope in Microsoft lingo. So that is parallelized, and we compute a distribution of thesaurus in about maybe 4 hours for Wikipedia on 60 cores. So that might easily scale up to large parts of, say, English web. Okay, so now we have this distribution of thesaurus, but since it's unsupervised and clustering, still it's hard to evaluate, how to assess quality. Since we didn't know how to evaluate this kind of thing, we set out to invent a couple of evaluation methods and check whether they agree. Yes, please.
So speaking of evaluation, on the previous slide, did you evaluate each, like for example, did you give any statistics about how many tuples were extracted correctly versus incorrectly or partially correctly? Or did you just evaluate the whole end-to-end?
In this case, we evaluate the whole end-to-end thing. Of course, it's not that all tuples are correct. Other evaluations showed, please correct me, Dick, if I'm wrong, something in the ballpark of 80–90%. Yeah. I mean, it also depends on what tuples you go for and what is your list of tuples. So we're pretty okay with subject-object relations and noun coordination and compounding, which we all use. Distinguishing obliques and adjuncts is kind of hard, and we don't know whether there is a difference at all. So it's kind of a hard question. So there are evaluations like that in Powerset, but not for that specific purpose. Okay. So we dreamt up 4 different evaluations directly for distribution of thesaurus, which is a visual evaluation. We should give that to team members. A couple of entries, a couple of distribution of thesauri, and check which one looks best. Very informal. We also measured word-net overlap. So for a large number of nouns and verbs that had entries in the distribution of thesaurus, we checked the word-net distance, and we used Jing-Conrad measure for that, since it has been proven useful in many tasks, and checked for the top, say, 10 entries. What's the average distance in WordNet? And we would like to get the distribution of thesaurus with the shortest distance, with the highest similarity. We also use this Turkonym rank. So what's a Turkonym? A Turkonym is a synonym elicited by Amazon Turk. It's a very simple Turk task of you give a word and ask Amazon Turk to return a list of synonyms. So people would just enter synonyms, and it's pretty good what comes out. So we have like 250 pairs here, a very small experiment. And we check how often we can find them in the distribution of thesaurus and how highly they are ranked, because what we want is similar words, and synonyms are clearly similar words. And we also implemented the most frequent sense finding method of McCarthy et al. This is basically taking a distribution of thesaurus entry and checking in WordNet what sense is most frequent by checking overlaps of like different regions where you can find that senses of the words, and trying to find the highest one. And we labeled up a couple of sentences ourselves, random sample, to get an idea what is the most dominant sense, and try to check whether we can find that back with that distribution of thesaurus. And what we found somewhat surprisingly, that all 4 methods highly agreed. So even though they're kind of different, I mean, Turkonym rank and WordNet overlap is a little similar in the way that WordNet also contains synonyms, but what we found is that we can safely use the automatic methods, which would be WordNet overlap and Turkonym rank, and not doing all this visual evaluation and sense distribution labeling, since they give the same results. And this is unfortunately only evaluating that distribution of thesaurus and not the whole system. But since we had too many parameters for that thesaurus, we tried to like step back and do that first and get some rough idea what could be good. So what came out of that was, if you want to compute a distribution of thesaurus for that purpose, per word only use the 200 most significant features. You could use 300, but don't use much more. And the more frequent a feature is, the less weight it would have. So it's much more, giving you much more information if you have a really rare feature that applies only to a bunch of words than a very frequent feature, like she as a subject or large as an adjective modifier, stuff like that. Okay, so now we have an idea what distribution of thesaurus to use. Now we can go ahead and cluster it. And just as we saw with that HIP example, the idea is that similar words in that distribution of thesaurus entry cluster together because they are each other, they are contained in entries of each other and have a similarity score. And yeah, just like in the previous examples, cluster will serve as dense representations. And I used to build a context model. So we can collect the features of the words we find in the cluster and aggregate them up and use these in the context-based disambiguation. For clustering this, we use Chinese whispers graph clustering, which has a bunch of nice properties. First and foremost, it finds the number of clusters automatically. And this is crucial for word sense induction. You can't just set out and say, okay, everything has two meanings. And then you have a word like father, which is super frequent, but it just has only one meaning, basically. So another thing is it's very efficient, so we can easily do that for a wide range of the frequency spectrum. And it's proven useful for natural language data in general because of natural language. So graphs induced from natural language usually have properties found in social networks like scale-freeness and small world like clickishness, and that all comes in handy for that clustering algorithm. So let me show you an example for our best found distributional thesaurus. We clustered the entry of arm as a noun and used the first 100 entries for that. And what we found is we get three clusters here. One is mostly body part. If you look closely, you could probably find things like armchair, arm. And yeah, since it's 100 words, of course, this is quite far away from arm. Some of them, like mirror. But anyway. Another cluster here is much smaller. It's firearm. And the smallest is branch, or yeah, the arm of the branch of the company.
Adjustable rate mortgage.
Huh?
It's an adjustable rate mortgage.
Rate mortgage?
Yeah, it's an acronym.
It's a financial term.
Oh, is it? I didn't know
Yeah,
that.
yeah.
Oh, that's good. Yeah, I was wondering.
Which means boom is the outlier.
Boom is the outlier. Okay.
Not at the time it was clustered.
That's true.
No,
Yeah, bear in mind this is Wikipedia, so all that things of yeah, we've seen that recently a lot in news. Doesn't affect this, right?
But I suspect hammer is arm and hammer, the company in the first one.
Okay, so that might be a natural, like a named entity recognition issue, which unfortunately this is also our group, so I can I cannot blame anybody else for that. Yeah.
So, I have a question about, so you mentioned this distinction in the learning distributional similarity between things that are synonyms and things that are similarly distributed but are not synonym with each other, like body parts or
Yeah.
colors or...
Right now we cannot distinguish them.
So
Yeah.
that's an interesting problem, so I was wondering if you had like any...
Yeah, I have something in the further idea section about that, but it's like a crucial core problem to everything like ontology, learning, and taxonomy, induction, and so there's a huge body of research about that, and nobody ever came up with a really good solution, I guess.
At a very practical level, so Live Search has this problem with as well, because they do a lot of induction on queries and logs of for suggestions of a whole number of things, and they can't tell the difference either. Things that are just distributionally similar but not synonymous.
Right,
in
right,
many
right.
cases they're antonyms.
In the query alteration project, for example, yeah, if it's just two companies manufacturing the same thing, but you clearly, if you look for one, you don't want the other. It's like this PowerPoint Excel example. Yeah. Okay, so let's look at the features we get from these clusters. So the body part feature looked like, you could attach something to it. It's coordinated with leg, so arm and leg, or neck and leg. You can have it, you can break it. It's coordinated with body. It can be long, it's round. So these are the most frequent ones. So here's the frequency counts for that. For firearm, they look entirely different. And it's also striking that the kind of feature looks different. So the first part is always the kind of feature we have. So these are more the coordinations with other nouns, like arms and explosives, or arms and ammunition, and you can grab it, you could use it, you could hold it, you could equip something with it. And for that branch, or what was that, mortgage?
Mortgaging is another one.
Yeah.
Looking at this list.
So that looks more like the charitable arm of the company, right? And I mean, we're going to have the problem that these kind of minor senses might get conflated together or just skipped out. But on the other hand, this is minor senses. So we have very low counts here. That means we have very low confidence here. That means for that low confidence stuff, we better leave it out. We don't expand, right? Maybe we start with the low-hanging fruit of the big senses first, and just have a method of detecting whether or not we should do it. And yeah, if you have a constructed sentence like this, like the commercial arm of the company produces arms and guns for people that broke their arms, then it's pretty clear that you could use this grammatical context here to disambiguate. Oh yeah, this is like a slide that illustrates how to arrive from these clusters to these features. So imagine we have that in place. It's currently being coded. Now we want to, again, evaluate it. And for that, we set out to build a sense-labeled evaluation corpus. And it's a little different kind of corpus as what we find in repositories or in the literature, because basically what we want is sentences containing a target word, which is marked up as such, and we want to know whether this group of sentences, like we want to have groups of sentences that contain the word in the same meaning. So we're not interested in a positive definition of that meaning, or a class, or like a definition, or we just want to like distinguish these meanings in the first place. And what we would like to have after that for our search application of semantic expansion in the index is we want to have these substitutes for these target words grouped by meaning. So what is like a viable substitution given that we know the meaning? What we would like to have is that the distribution and the coverage of senses should be the same as in our target collection. So it should match this underlying corpus we draw these things from. So this is another argument against SemCore. And these senses should be grouped by the same substitutes and not by the same entities or whatever you might think of as being viable distinctions on a semantic level, which is, of course, having a lot of granularity. So coming back to that hip example, probably we do not want to group together the clothing hip and the medical hip because it's different substitutes. Probably we won't. Like, I'm not sure about that yet. So this is a Turkonym bootstrapping acquisition cycle that allows us to get an evaluation corpus. And we actually executed that for a bunch of high frequency words as a pilot. So we start here. For each word runs through that circle until it finally finishes. Each word we draw a couple of sentences that contain that word from our corpus, and we try to get different meanings. For that we can use any word sense induction disambiguation system we have in place. In this case we use that bag of words one. That's not crucial, but it speeds up the process a little. Then we have a low number of sentences, say 10 sentences, and we get Turkonyms and contexts. That is, we present a sentence with a marked up word to Turkus and ask them to supply synonyms in that context. Then once we have these sentences with Turkonyms, we can cluster these sentences according to their Turkonyms. So putting these sentences that get the same substitutions in the same cluster, and for each cluster we take the most prototypical example, however we get it. So we aim at one sentence per sentence per usage. Then our corpus comes in again, so we select, say, 100 random sentences from the corpus and have Turkus match the meaning against these one sentence per sentence. And we also give them an exit. We give them an exit, say, no, it's impossible to tell because that sentence really is too short. Or we give them an exit telling, oh yeah, it's not covered in these sentences. So the new sentence that comes in is not in the sense model we already have. If we could reliably assign most of these sentences, then we assume that we captured most of the sentences in that corpus, so we're done. If we have a lot of uncovered, we send them up here and repeat and go on like this. So this is how the Turk tasks look like. Again, a little small, but it's a simple task. Like here is like this find substitutable words, a sentence with a bolded word, and they can enter substitutes. And we would pay them 1 cent for completing this. For match the meaning, it's much more instructions, and then we have a sentence, marked up word, our prototypical sentences, plus the 2 exits, uncovered and impossible, and we would put 10 sentences of these with the same target word in one hit and pay them 3 cents. So this is really, really cheap. But still, it's quite reliable. So for case, it came back at some point with 2 sentences. If you iterate longer, you get more maybe. So that was the states and trade unions involved in the case. That's the jurisdiction case. And if you look at these cases that have been aligned like that, it's all the jurisdiction, like the lawsuit case. Whereas this one is an interesting one. For cases of fabricated evidence, so that bag of words model would probably assign a lawsuit there because it's fabricated evidence, which you can find in the courtroom. But of course, this is like the case that's in situation. And these are all reliably marked up here. And we want to use this as an evaluation corpus first and foremost, but we're of course also looking into using that for supervised word sense disambiguation system and training. But we're going to see results of our other system first. So what we currently have is for about 100 words, sentences from about 15,000 articles, and this has about 70,000 sentences, which total about 110,000 interesting tuples, so tuples that contain our target word, and that costs us about $300. So this is really much, much less than what went into SemCore or other kind of things. And it's not that elaborate, but for our purposes, that's pretty much what we need. And these things we're going to use for evaluation. I'm slowly coming to the later and later stages. So right now I'm talking more about things that we want to do as opposed to things that we already did. And this is how to tackle these substitutes, right? Because we get substitutes here. I mean, from this process, we get all these substitutes. We could use them, but we only have that for evaluation corpus. What we want to have is substitutes for all words. And what we can do is, in a first system, to map that up with WordNet. And that might be even desired, because there's a lot of NL pipeline steps and other resources like FrameNet and Sumo and I know what, that are mapping to WordNet. So sometimes it might be advisable not to construct everything from scratch, but to take what's there and align it to it. And there is this method that I mentioned earlier by McCarthy et al. That has been used to determine the most frequent WordNet sense using a distributional thesaurus and looking at the hierarchy and seeing where the words of the entry come up and what is closest. And once we cluster this distributional thesaurus entry, we could do that not for the full entry, but for the single clusters, and maybe get some idea how to map WordNet senses to cluster senses, which will not be at all trivial because the granularities do not match and distributions do not match, but there's at least some path to it. So for our ARM example, there's this part of WordNet that has ARM as branch and subdivision, which is a kind of division, and there's ARM as a weapon, and it has hypernyms, a couple of weapons, and it's a kind of instrument. So if we overlay that with the cluster we saw, it's pretty clear which sense WordNet sense is meant here. And once we do that, we could use the substitutions that WordNet gives us. So ARM N3 would be substitutable with weapon, and ARM N4 would be substitutable with branch and subdivision. And if we would match query and passages, we might even use hypernyms and all the things we currently do in the Powerset search engine. There's a question?
What do you do about the cases where words have hypernyms that are not included in the WordNet collection? To an example that Lucy and I played with is, tulip is not a flower in WordNet.
Oh, is it?
A rose is a bush, but it's not a flower. You won't get to it.
Yeah, there's a lot of awkward things
so
there.
How do you handle those cases? Because they must be
in our first system for the substitutions, we don't handle them. What I would hope is to find a way to get all these substitutable things from the corpus, either entirely in unsupervised or weakly supervised by training that up with existing things or having Turkers tick off the good things and throwing out the bad things. And I think this is the only way to go in the long run, because we want to adopt that to other domains, other languages, and so forth, and also make it extendable to new lingo and terminology, which is clearly not the case if you have a fixed inventory. And also, we are not concerned with it right now. We're keeping that in mind. And one thing is to probably use several data sources. So in the meeting before, we saw this interesting similarity lists, like paraphrase lists coming from machine translation, which look pretty much similar to these distributional thesaurus entries in a way. And you could also think about pattern-based methods like Hurst patterns. So bluntly looking for X as is a Y, and combining that with these sources, because these very shallow pattern-based things, they hit a couple of good things and also a lot of noise. But the more sources you combine, the better you get at the real picture, we would hope. That was a question.
How much do you have left? Because it's more of a suggestion, actually.
We're getting very close, so maybe we could do that in the discussion. Sure. Yeah, I'm already in the further ideas. So the pattern thing is up here. Another thing that is up here is confidence first strategy is like disambiguating only the really safe bets. So we have like a lot of trigger words, and we know exactly, okay, this must be that sense. And once we have that, we can learn new trigger words from these occurrences to self-train the model, and even use other triggers like domain-based triggers or just bag of words features along these lines. And we could also use Turkus to align a word net with our sense inventory if we want to. And we can also use Turkus to join senses in WordNet, because WordNet is kind of too splitty. It makes too many distinctions for IR. So immediate next steps would be to evaluate how much we gain from that grammar features. We want to assess coverage. We want to directly evaluate that WSI and SD, so induction disambiguation with the Turkus, and eventually do relevance testing with that. But for that, we might need a targeted passage and query pairs. On the front of feature engineering, we want to experiment with more and more precise grammar features, and maybe include these topical features, trigger words, or even like domain information. So to conclude, I showed you a data-driven approach to word sense induction disambiguation, which is characterized by minimal manual development, because the inventory is induced and it needs only a parser. But even if you don't have a parser, we can always fall back to a bag of words. It is possible to map that to existing inventories. I showed you some evaluation strategies, the next step. So this is the end of my talk. I want to thank you very much for your attention. I'm open to questions and comments, and thank you very much. So that was this suggestion.
So if there's a concern over finding words in this list that are safely substitutable, so you mentioned one reasonable option is to try to find overlap with patterns that also indicate substitutability.
Mm-hmm.
An idea I think that sometimes gets lost is there's actually very clear patterns that indicate the opposite of substitutability. And you can mine for those in text and do the sorts of tricks like bootstrapping. Once you find a few words that aren't substitutable, you can find where they occur, the syntactic patterns that they occur in. Because Excel and PowerPoint actually co-occur all the time.
Right.
Patterns that will tell you that you should never substitute them for each other.
Like what kind of patterns?
Yeah, what kind of patterns?
Stuff like and.
And?
Other than the is a, such as,
Right.
and.
That would qualify them as siblings, right? Yeah. There's even a work on. There's even work that boils that down to if you have a high frequency word between X and Y, and you see them also in the other direction, then they are siblings. That's a ACL 2006 paper. I was really impressed with that. It works like for 20 languages at least. Yeah. Yeah, that's a good one. That's so we can learn a lot from all that ontology induction literature, right? Just even trying to get the relations right, because if we know that, we might mine for what is the common hyponym, right? Yeah.
I know that a lot of the people in this audience are interested in ontologies.
Uh-huh.
Is there a follow-on story for ontology induction?
I digged into ontology induction a couple of years ago, and I bailed out and thought it was not worth the trouble, because what in the strict sense of ontology as a formal ontology with all that entails, like you want to do induction on that and inference and a lot of things. And what I saw so far is that there's these top-level ontologies that come from top-down, and these kind of methods would come from bottom-up. And there's a gap, and this gap is not easily bridged. So you could probably do something like population. So if you have quite a good skeleton, a good taxonomy, you could find, say, instances. You could put in named entities in the various places. I think these kind of things would work. But constructing that bottom up from scratch will not lead you to the top level domain, because these things are not expressed at all. And I think humans do not learn that via language, but via interaction with the world. And that, if you look in corpora, that's just the part we're missing. That was a very high-level ontology view.
So ontology induction is building ontology from using natural language processing to build an ontology.
Well, it depends on what you. Oh yeah, I'm.
Ontology induction.
Yeah, I was speaking about first getting that taxonomic backbone that is always underlying ontology by looking at text and applying NLP methods to get at this. Yeah. But that doesn't mean that we should not try. Right?
Do you use ontology settlers? And Powerset is sort of looks like you represent the extracted information as in ontology structures so that you can query on things. Do you?
Not explicitly. What we do is we query Freebase, and we extract a lot of facts from Freebase, and Freebase is kind of a big database for, say, named entities and a lot of data on them. So we have a component that tries to translate a query into a Freebase query. It's kind of a natural language interface to a database, so to speak.
Right.
And we would get this, what you call an ontology from Freebase. We don't maintain our own ontology. What we do is we do something like instance classification into the WordNet hierarchy. And currently we're using mostly WordNet hierarchy.
Thank you very much, Chris. And I think everybody knows the email address, so please continue to ask questions. Thank you very much. I think that unsupervised methods and induction of word senses are very, very, it's one of the most interesting new directions of the field. So thank you.
Thank you.